Um, so yes, I'm going to talk about artificial intelligence and brain imaging today specifically. Um, it's a hot topic in the neurosciences. And is it really going to be Panacea's potion or more like Pandora's box? And if you um, look at some of the current literature that's out there in your neighboring bookstore, they view it as a much more dystopian future. Will artificial intelligence destroy us or save us? And does it mean the end of an era? And we'll talk a little bit about this today. In full disclosure, the bottom three, Avicenna, I'm a stockholder in this startup company for artificial intelligence. I'm working with Subtle Medical, another startup, and Philips Healthcare on some AI related projects. So in full disclosure, there will be some of those things in this talk. We'll briefly talk about artificial intelligence, how we got here. We will talk about its applications in radiology by going into some of the methodology, specifically deep learning and convolutional neural networks. We will lean into some of the validation metrics and then end with a few notes of caution so that you can evaluate the literature yourselves, and especially with respect to bias and ethical issues. And then I'll give you advice if you are going to buy some AI imaging products yourselves. What are the advantages to artificial intelligence in imaging? Machines don't get burnout. Their eyes don't suffer from fatigue. They can detect things on an image that are not perceptive to the human eye, which we'll talk a lot about more. It may be a way to provide decision support to help with diagnosis. And I think the more exciting thing is its predictive power with respect to genomics and treatment responses. If you look at the journals like literature, there's been this exponential increase in articles on artificial intelligence. And most of that is being driven by neuroimaging. And I'm a little bit biased as a neuroradiologist. It always starts from the head and works its way to the rest of the body because the brain is the most important organ. My friends who work for Wall Street have sent me this slide from PricewaterhouseCoopers where artificial intelligence will be about 14% higher in 2030, the global GDP that is, of that $16 trillion of economic gain potentially. But how did it all start? In the 19th century, George Boole came up with this concept that data could be rendered in one of two states, binary. That underlies the development of electronic circuitry in the late 19th century. It underscored the development of Boolean logic, right, with algebra. And it allowed for the development of computer code. So he is really how this all got started. Now, this is the father of artificial intelligence, Alan Turing. There's a great movie called Imitation Game. You should watch it, although it's only about half accurate. But he is really considered the godfather of this because back in the 30s, he came up with this article. And he basically was wondering if he could create a machine and write different instructions that it could do different things, improve mathematical algorithms. So that was really fundamentally important because up until the 30s, a machine was really built to do one express function, like a coffee maker just made coffee. And what he was basically saying was that if I wrote a bunch of different instructions and gave it to this machine, it could do multiple different tasks. And that is what a computer does. And so he sort of invented that conceptually. And shortly thereafter, World War II broke out, and he was sequestered by the UK government in top secret to develop really the first computer called the Turing machine. It broke the German Enigma code and really was this reason why we succeeded in cracking that code and defeating the Nazis in World War II. This is what it looked like. It's on display in Manchester, United Kingdom in a nice museum. Then in the 50s, he came up with a much more important intellectual mathematical concept. Can machines think intelligently like a human? Again, he really wondered if you could create computer algorithms that would get a machine to think like a kid. So for example, my 2-year-old would drop food on the floor from his high chair. So he's learning Newtonian physics, and at the same time, secondary gain is my dog would eat it up off the floor, right? So, and then he would also learn about like thermodynamics laws, like by spilling his milk and saying that entropy and chaos ensue much more easily. And he wondered if machines could do this. And that's why you have these things called Turing questions. So if you were ever on a phone and you want to think, is that a bot or a person? You could ask it one of these questions, because a lot of these questions, bots and computers have a hard time answering, like how does love feel? Or which came first, the chicken or the egg? You probably come up with your own questions. Try it out on Alexa or Siri at home. In the 50s at Dartmouth, you had these 4 computer scientists, Minsky, McCarthy, Shen, and Rochester, who were really doing groundbreaking work on computers in the 1950s, believe it or not, all on artificial intelligence. And they came up with this declaration that all information in the universe could be rendered binary. And they thought they could accomplish some of these things in the summertime, making significant advances. In 1957, Frank Rosenblatt was a graduate of the Bronx Science School, so cheers to them, one of these great public high schools of science in New York City. He developed the first sort of artificial intelligence machine, if you will. It was an artificial neural network. It was a simple machine learning program trying to distinguish a cat from a dog, a sort of a binary classifier imaging recognition tool. It was patterned after the Calquine cortex. So you had these different inputs, which were features of an image. They were weighted differently. It produced an output, went through an activation function, meant to simulate how our neurons think in the visual cortex, and then it would make a prediction, is it a cat or a dog? And it was sort of something like this schematically. You try to separate the dogs from the cats. And in 1959, MIT started the first AI lab in the US. The first robot was working in a General Motors plant in the early 60s, and natural language processing, which you hear about all the time, was first developed in 1962. And the first chatbot was Eliza at MIT. And this is a transcript from one of the first conversations. And it didn't work particularly well. The chatbot was supposed to be a psychotherapist. And invariably within a minute, it would fail. We just did not have the kind of sophistication that was needed to render that feasible. Now, culturally, as there was a lot of discussion in academia about artificial intelligence, you know, Hollywood and the great thinkers and the arts were kind of alarmed by artificial intelligence back then, and they developed this really classic movie. If you haven't seen it, I highly recommend it, Space Odyssey 2001, in which HAL, which stands for Heuristically Programmed Algorithmic Computer, because remember, computer code is all about the algorithm, does a couple of pretty terrible things to this people on the ship. I don't want to spoil the movie for you, but I would recommend it highly. It was inspired by the work at MIT and that chatbot, Eliza. Now, as computer science was taking off in the 60s, there were definitely some drawbacks. There were a lot of things that were being posited intellectually, which couldn't really be tested very effectively because you didn't have the appropriate computer processing power and or speed at the time. And it was only, in the 70s that IBM was investing millions into this. What I'm showing you is a microchip, a silicon microchip, which underlies computer processing, right? And that wasn't really being fully adequately developed. It was not keeping pace with intellectual diagrams of artificial neural networks, for example, or machine learning. And that sort of created a kind of AI winter where things weren't funded as well. But, still some machine learning programs developed in the 70s and 80s, but AI took a bit of a backseat because of that issue, which we'll talk about in a little bit. Now, why would I have something like this on my PowerPoint? Now, this is a Kraftwerk, this band from Germany. Now, in the late 60s and early 70s, long before most of you were born, it was absolutely revolutionary that you could have a rock band that wouldn't use a single instrument like drums or guitar or bass. It was completely made up of machines making sounds. It was synthesizers, and these were engineers, a couple of them in this group, who created their own instruments, and they used computer programming to make some of their melodies. So for example, in this particular case, in German it says, Ich bin der Musikant mit Taschenrechner in der Hand, which means I am a music maker with a pocket calculator in my hand. And it sounded something like this. So I recommend that you download that music if you'd like, but they computer program some of their melodies. And they still are not accepted into Hall of Fame of rock and roll in Ohio, but I would contend that they belong there, given that the entire disco era and synthesizer music of the 80s can be traced to their influence. Back to the world of AI. So as that was going on culturally, musically, there was a lot of work being done on imaging analysis with artificial intelligence, specifically machine learning, textures and fractals, look at an image and make statements about it. Like, for example, this is a meningioma undergoing fractal analysis, which can predict an atypical from a typical meningioma, work that we published a few years ago at Northwell. Decision trees and support vector machines are different kinds of machine learning which can be used in image processing tools. Now, Jan LeCun, who's at NYU currently, was at Bell Labs in the late 80s. He developed the first convolutional neural network, and he was working a lot with Yoshio Bengio, University of Montreal. These are two luminaries in the field, along with Geoffrey Hinton, who also is publishing about backpropagation, a way to sort of develop a convolutional neural network. And this all may sound like gibberish to you, but we'll get to this in a little bit of detail shortly. And if you have any questions at the end that I do not get to, I will have my email, and please email me, and I'm happy to have a conversation with every one of you. This is an example of convolutional neural network, and I'll get into a little bit of more detail in just a moment. But this was published in 2006. It was, he's from the University of Toronto. It was cited over 10,000 times, and basically it was a novel computer architecture meant to simulate a human brain. And we'll get into this in a little bit more detail now, because this started the big bang of AI. And I want to finish up some of the history, and then we'll go back to the specifics of that convolutional neural network. But in 2006, why? Why suddenly was this the big bang of AI? It's because of all of you computer gamers out there, because you wanted to have faster, more realistic three-dimensional computer games. And because of that, we had to do something called development of GPUs. So NVIDIA Corporation in 2007 pioneered this graphic processing unit with thousands of cores and parallel processing. So it's 40 times more powerful and efficient than your basic CPU. Now you have this way to analyze data much more quickly and efficiently. That was a big deal. So then we can get back to this. And they use that kind of GPU and that kind of CNN computer code development to develop IBM Watson, who beat the Jeopardy champ. In 2012, Alex Rajewski was working with Hinton, University of Toronto, and he developed ImageNet classification using a convolutional neural network. So at that time, they would have these contests where they would dump millions of images into the internet, and who could come up with a program that could classify those images. And after 2012, every year it's been won by a convolutional neural network. And in 2016, it surpassed human level performance. So it does better than people at classifying images. So I'm going to show you some examples. So, well, that's the architecture, which is always important to look for when you're analyzing the literature. But in 2012, Dean was the head of Google AI. So he actually developed this a network of 16,000 processors, 1 billion connections. Now our brain has like 10 to the 11th, so it's still not a human brain, but getting closer. It browsed YouTube, 10 million looks over 3 days. It was exposed to 20,000 images and got cats correctly about 75% of the time. But you could do much better than that if you actually come up with a much better architecture and code. And that has happened subsequently. So this shows you what it's like. These are sort of test images. And these are basically images that are trained on, and using that, it'll make a prediction as to what an image is. So for example, if you show it a mite, it'll come up with that answer correctly, but sometimes it doesn't do so well. So again, the data you put into your program, your convolutional network matters. We always have these expressions, garbage in, garbage out, but you can see here, for example, it had a harder time getting the car, went to the grill. Here it focused on the Dalmatian and the spots and not the cherries, and did very poorly with the lemur, or the Madagascar cat, I guess is what it's called. So the point being that you're only as good as your computer architecture and code, and the more data to which something is exposed, the better it will be, and especially if that data is curated or annotated. So here's a classic example. Computers have a really difficult time telling the difference between Kentucky Fried Chicken and a little baby golden doodle because they look too similar. There are other images out there on the internet where you look at the top of a blueberry muffin and it looks very much like a chihuahua head. So it doesn't do so well with these kinds of distinctions. And lastly, Go AlphaGo. This is a really big game in Asia. There are more atoms in the universe. Well, actually, there are more Go game positions than there are atoms in the universe. My wife is Asian. It's a big, big game. And this was basically a convolutional neural network that was developed in North America, in Europe and Canada, North America, and teams from IBM. And it actually did beat the Go player. But there are a couple of very important lessons here. Number one, the Go player learned from that computer program. That computer program did a move that had never been seen before. And if you watch YouTube videos of this as it was going live, it's just really funny. You can hear all these people gasping when the move was made because they had never seen it before. But by watching that computer do certain moves, Lee Sedol, the world's best Go player, actually learned how to think more creatively outside the box and eventually beat the computer. And that was what a winning Go game position looks like. And lastly, I'll just finish up by saying these three names which I had mentioned, two in Canada, have won the sort of Nobel Prize equivalent of computer science. So let's get into the imaging of what I do as a neuroradiologist and how this may really transform healthcare going forward. When I look at the left, I see my dog, Mount Fuji, and a snowflake. I really don't need a computer program to tell me on an MRI image that that's a brain tumor, a hemorrhage, or an MS plaque. What I want it to tell me is whether that brain tumor is expressing certain mutations, which have a definite impact on treatment planning and prognostication. So when I see that dog, I see two legs, a fuzzy tail, a face, and my brain automatically says, okay, it's a dog. The computer sees a bunch of numbers arranged by 20 by 20 pixels. It sees a 400-dimensional coordinate where the computer essentially says, given numbers in this distribution on that picture, what is the probability that that's a dog? This is how the computer thinks. We went over this earlier, but just to reiterate it, these are different inputs. These are different features of that image. They're all weighted a bit differently, and you get into these hidden layers. And hidden layers are just a distillation process. You're distilling important imaging features or patterns, and then it's going to get passed on to this other layer, just remembering the things that were the most important to come up with some model. And usually it's one that makes it faster and more efficient. And then it's going to come up with an output and say, well, I think that's really a dog. And it's going to compare it to ground truth, that dog. And if it's wrong, it goes back and it reweights everything. And it goes through this process iteratively over and over again. Every time it cycles through, it's called an epoch. That's essentially how it works. And it simulates how our nerve cells work. So here's an example of machine learning. We have separate steps for feature extraction and training. And here is deep learning. Now, deep learning is just basically, these are all meant to simulate neurons in our head. These are all nodes. And they're all linked to one another. And there are no assumptions or hard-written rules. You expose it to data and desired output, and it's going to readjust and adjust this weighting until some sort of intelligence arrives. And it's really the theoretics of how deep learning works. And it does involve convolutions. So here's an example. You have inputs, these convolution layers and pooling layers. So basically when you convolve, you roll together. It's basically, convolutions just really refer to operations between two functions which result in a third function, and that third function just tells you how the shape of the two influence one another in that third function. And then you get these, you can look at it here, like it takes these little different pieces of an image, then goes to this network and it comes out with these outputs. And there's just an example of what convolution means, right? Sawtooth signal response, and that's when you convolve them together. So how does this mean? This is like the last big slide, then we'll get into a lot of imaging and practical clinical things. So if you're looking at this car, the first convolution may just look at the four wheels. You go through this activation function, you weight it differently. You go back, you may start looking at the windows, and you do this repetitively. Pooling reduces the number of parameters, right? So you don't have any overfitting, and eventually come up with your model, and you spit out these answers. And this is essentially what we're doing with imaging. So here's an example of a typical convolutional neural network called a GAN. And I only mention this briefly because this is very popular right now. And you'll read a lot about this in literature. And essentially, think about this as you're going to a bank and trying to pass counterfeit money, where I'm the counterfeiter, the generator, and I'm going to try to make bills. And they're going to be compared to real bills. And when I get really, really good, I can fool the discriminator. And this is basically how it works. You're setting up two different CNNs, which are going to compete with one another to come up with a better model more quickly. So what are some practical tips if you get into AI research? Well, you want to have a lot of data, more is better. The biggest important lesson I can give to all of you is you want to have a lot of images for training. You then validate it, then you want to test it on an independent data set or a holdout data set. And typically if I had like 1,000 images, I would use 600 for training, 200 for validation, and 200 I would hold away as an independent holdout test data set. You can't use your test set to train or validate. That will give you a bias and you'll overinflate performance. If you don't have enough data, sometimes you can skew it, rotate it, flip it around, randomly change it to get more data points. And you don't want to overfit. There are many examples in the literature where a program designed, let's say, for example, to predict sepsis, which is a really bad clinical overwhelming infection. What are some of the things that can predict it, like changes in blood pressure? When these things have been developed at a particular hospital and then they're not exported to another hospital, they tend not to do as well because there's a lot of heterogeneity in those data points, which they do not account for. And lastly, you want to have good hardware, GPUs, good softwares like TensorFlow, Keras, Python, a pipeline to extract images easily, and you want to have large data sets. And there are some that are publicly available, like Brain Tumor, NIH, the ADNI for Alzheimer's, and the Michael Fox Foundation for Parkinson's. So let's talk about where it's really important. There are tons and tons of really cool things happening now in imaging, which I want to show you starting currently. So the first thing is segmentation. For us to use AI, we have to be able to have these programs which segment out tumors automatically. You want to strip away the skull so you can't identify people. If I don't strip away the skull, you could potentially take this image and make a three-dimensional face and try to identify someone. So you want to strip away the skull, extract the tumor, the edema, the enhancement, and you use this dice score to see how good you are compared to manual tracing of these images. And this was a former resident of mine who won like the worldwide challenge and beat Siemens and IBM, which I thought was great. Or he tied them maybe, but anyway, he did a great job. And he's at UC Irvine currently running an AI lab. Here's an example of a convolutional neural network program, which is being trained to automatically segment the prostate gland here. I'm not a body imager, but that is the prostate gland. And it takes around 320 patients to actually have enough data to get a really good program to automatically segment. So let's talk about how we can use this. There's a ton of interest in using AI to detect hemorrhage in the brain on a CT scan. Dr. Ellis just talked about brain hemorrhage. This is a good segue. It's a big deal. There are 100 million CTs in the US done annually. It's increasing all the time. Most are normal. It's a big cost sink, right? About 1.3 billion per year per head in fees alone. And why do we want to develop this? In many parts of the world and in many parts of America that are more rural, you don't have experts in brain imaging to read images at night. So maybe it would make sense to have a program that could identify these things. Or maybe just to have a program that would highlight it on the pack saying like, warning, 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 brain hemorrhage has just been detected on a patient who is scanned, and it would go to the top of your work list and you get to it right away. So let's look at some of this. And why is this a problem? Because, well, there are lots of stroke centers, for example, where you have to have 24/7 coverage to look at that to make sure there's no hemorrhage. And I'm going to show you that in our own hospital from like January to like October 2018, we had this exponential increase from 400 to almost 1,800. It's like 4 times an increase in volume without any increase in the number of people reading those scans, right? So you can understand how we're feeling a little burnt out. So here's our first foray into this. We looked at 5,000 head CTs and we were very accurate and very high sensitivity, specificity, good positive and negative predictive value, good dice scores. And it only took 0.08 seconds for us to detect the hemorrhage like this. I'm going to show you some examples of the 2 false negatives on our first batch of 268. That little dot, I think even now, I don't think I would really call hemorrhage. I'm going to show you some other pictures in a second where it's a little bit easier. So this is showing you a bounding box technique, which is part of a convolutional neural network program that was developed by Peter Chang at UC Irvine. And basically, on this image, it scans all around the brain. It's looking for something of high attenuation or high density, something that looks bright. And it focuses on it, says, aha, I've detected it. And it zeroes in on that. And eventually it just says, okay, I've got a big blob of something bright here. This is going to be hemorrhage. And then it sort of outlines it out and it can spit out a volume. And it'll do this on every single slice automatically, and it'll spit out a volume of hemorrhage. And that's a really good thing. And we looked at this and published this a few years ago. We looked at it with parenchymal hematomas, epidural, subdurals, and subarachnoid hemorrhages. We had really good accuracy and sensitivity and specificity. Here's an example of true positives. It's really subtle subarachnoid hemorrhage, a really subtle extraaxial hemorrhage being picked up by our artificial intelligence program. You can get false positives occasionally, typically from beam hardening artifact like here, or because of a straight or dural sinus blood being a little bit hyperdense, or dural calcification. So there are some caveats. It's not perfect, but overall, this was looking at, I think, 10,000 CTs. We had really good accuracy. and really good negative and predictive values. So now the thing is to try to do this in real time and prospectively validate this on an ER scanner and integrate it into clinical workflow. There are more than a dozen companies now currently offering these kinds of products, and they're being tested in real time, even at Northwell, a company in which I have no interest, actually, so there's no conflict of interest there. Now, let's talk about glioma, and this is Dr. Bookfar's big interest at Lenox Hill. He's running a lot of clinical trials, and we do know that for brain tumor, genetics are really important, and there are two big publicly available databases where you can actually look at images. The molecular features of a tumor are part of the diagnostic criteria for the World Health Organization. So for example, we know that most oligodendrogliomas have 1p19q co-deletions and a mutation of isocitrate dehydrogenase, an important enzyme on the Krebs cycle. We know that they correlate with histopathology. There are different kinds of primary brain tumors that we call a glioblastoma or glioma. You can have classic pathology, they could have neural, proneural, mesenchymal, and those different histopathologies have different molecular features which will influence your longevity and progression-free survival and how you respond to therapy. One of them is epidermal growth factor. If you amplify that, you have a much more vascular tumor, your prognosis is poorer. IDH1 mutations are good and they're associated with favorable histopathology. Also, you have MGMT, which is, if you have that mutation, you'll respond to therapy better, but you also have a complication called pseudoprogression. These mutations also have a favorable prognosis. And also these correlate with tumor location. So here's an example. We developed a CNN to look at primary brain tumors. We had 260 patients and we looked for these different genetic markers like MGMT promotion, this co-deletion, IDH status, and overall survival. We used FLAIR, T2, and pre and post contrast images. These are what all those images look like. We fed them into the computer model. And this was our architecture. It was a generative adversarial network with feature matching. You have these different convolutions, these activation function, and then you have this fully connected layer, and then we see how well we do. And with this fully connected layer, you can actually go back and look into your black box and retro-engineer and figure out what parts of the model were deemed the most important to make your prediction. And then this is the actual code that was written. I won't spend time in that, but I'm happy to talk about it offline. When we looked at our data, we had really good accuracy. And you have to think that this is pretty dramatic. We're looking at a preoperative brain MR before that tumor was removed, and we're able to predict with over 90% accuracy these genetic markers. It's much higher than that now. They're all above 90%. And that makes a big difference because genetic testing is not widely available and is very, very expensive. And it is really critical to getting patients into the right clinical trials and the right treatment. And it took about 5 seconds to do. And this can be incorporated into the packs. Now, when you look at these sets of images, to be frank with you, some of them, they really don't look that different to me. When I look at these, it's a coin toss. If I had to tell you, what is it preoperatively, it would be like a coin toss. I don't think I could do it. Or what about these images? I mean, this to me looks just like that. I mean, there's no way they look that different. So again, the critical concept here is that we're using artificial intelligence to augment my intelligence. To me, AI means augmented intelligence. You're actually improving my performance and making me better than I am. And I think that's really the goal. Because if I become better, I do better for patient care. You could do these heat maps showing you the probability distribution for certain genetic markers. And here's an example of 1p19q co-deletion. Again, these images on the left and right don't look that divergent to me. They look very, very similar. And again, the MGMT promoter gene, I mean, to me, these look pretty similar. I mean, there's some subtle differences, but this just looks like, this does not look different than that. So, I mean, I have a really hard time. And again, for me, it's a coin toss if I were to do this. And we're actually going to do that study going forward this year, I hope, with a multi-institutional approach, including Northwell. How good are we at predicting the genetics and how good is the tumor? Now, we also care about survival. If you had a program that could tell you really accurately that you had less than 6 months to survive, you may opt for different treatments than someone who has predicted to be more than 2 years or not. What's important about this study that we did is we actually looked individually at different factors that have been reported to associate with longer term survival, like the location of the brain tumor, how large it was, the volume of the brain tumor, this Karnofsky clinical score, and how old you were. But when we looked at those things individually, none of them mattered. But if you combined all this clinical information into that convolutional neural network, we had about an 80% accuracy in predicting a long-term survivor of more than 2 years or the poor survivor of less than 6 months. And to me, these images are really fairly similar. So I think this is a step in the right direction, and really where we want to take AIs. Can we make really good predictions about treatment response and outcomes? Another really big thing that's a big problem and a really critical unmet need in patients with glioma, and certainly, you know, Dr. Bookfor, it's a key interest of his. Can you tell when patients are responding to therapy? Because sometimes it looks like they're getting worse, but they're really getting better. And it's this concept of pseudoprogression, where you are giving patients appropriate treatment, but they come in, their scan looks terrible. It looks like they're getting much worse, although clinically they look okay. And that's called pseudoprogression. And it's really important to try to distinguish the two, because if they're getting worse, then they may fall off the treatment that they're on. They may not be eligible to stay on a clinical trial. So these things are really life or death decisions. And so we looked at about 100 biopsies, and all these squares represent probabilistic determinations of whether we felt that there was more tumor or more necrosis on the biopsy. We're about 80% accurate predicting this pseudoprogression. And you can make heat maps on the brain showing we think there's more necrosis in blue, more tumor in yellow. And that's useful. Okay, so how else can we do things? Well, I don't really like looking for aneurysms because they're hard, it's tricky. I spend most of my time doing research and do clinical work 2 to 3 days a week. Maybe I'm just getting old and rusty, but if I had a program that could say like, hey, that blood vessel in the brain doesn't look normal, I would love it. So computer-assisted detection of an aneurysm, I think it'd be great. I won't get into the details of this too much, but we looked at this from an MR angiogram with one of my former residents at Columbia, who's now Memorial Sloan Kettering, doing great work, and recently, I think, was given some grant funding. We developed a 20-layer CNN and at 500 images and had like 98% accuracy in detecting aneurysm, but not so good at estimating the volume of aneurysm. And I'll show you some pictures. This is what a UNet architecture looks like with contracting and expanding features. But here's the aneurysms that we identify. And you can see that it really should be here a little bit more. It's probably shouldn't be all the way over there. So, I mean, it identified them reasonably well, but we have work to do to actually get a more accurate volume, but it wasn't bad. The area under the curve was good. But here's a much more relevant study that I think is really much cooler. It looked at aneurysms and used clinical data and tried to predict which ones would rupture within a year. And they created a model where they put in all these different clinical factors and the images, and they actually were 95% accurate in over 590 cases of predicting which aneurysms would rupture. And that to me is really useful and really cool and could drive the science of aneurysm care. Now, this is the part that is really exciting to me, because how can we make MRI scanners faster and better? And this is a super hot topic. There is a big MRI meeting every year annually. There's a whole session devoted to this. How can you make MR faster? You can do this thing called compressed sensing, an undersample case space, combine it with a deep learning program, and you can have really super fast MR, 2 to 3 times faster with no loss of image quality. You can do an entire brain MR scan in 5 minutes and then get and extract from that the contrast that you want to see. You could do entire spine MR exams in under 10 minutes. And these things are being tested currently. This is not far off. This is actually happening as I speak to you, and it's going to revolutionize imaging. And it will absolutely lower healthcare costs because you don't have to pay as much for a 10-minute scan. It'll improve access. So I think that ultra-fast MR is the ultimate value-added proposition. It'll make imaging in healthcare, I think, less costly, because I really do strongly believe in universal healthcare, and this is one way that imaging could help achieve that. This is what the architecture of the code looks like. For the computer engineers listening, you will love this. These are what some of the images look like initially, right? You're trying to simulate. This is what a case-based map looks like. This is how you derive MR images. And this is like, you know, with different iterations, you get really close to approximating what these images look like. Now we can go one step further. So this is borrowed from my friend Greg Zaharchek and Enghao Gong, who have a company, Subtle Medical, where they're actually developing deep learning to do really super fast scanning with high resolution. So normally this is like the typical brain MR scan where you have what we call a sagittal T1 weighted image. It's looking at anatomy. It typically is done in the sagittal plane like this, and it takes a long time. What you could do is scan it in half the time, use a DL program, and generate a synthetic image like this, which looks as good as that in the same amount of time. And this is where we are now in the field. So you can essentially get an equivalent scan in half the time with no loss of information and better resolution. How can you apply this to something like arterial spin labeling? Now, this is a very advanced MRI sequence, which is looking at blood flow without using contrast, which is a big deal. You're just using intrinsic moving speed of blood. And you can take a very noisy image, and this is the root square mean error. So it's a really noisy image. You can see there's all this like stuff out here. What is all that signal out here? It's outside the brain. That's not good. And if you combine it with some other anatomic images, you can generate a synthetic arterial spin labeling image with much better anatomic resolution. Threefold improvement in this, 4-time reduction in scan time. That is a win-win proposition. My favorite is this one because people don't want to really give contrast. It's expensive. There's a worry that it may deposit in the brain, although with macrocyclics, that's probably not so likely. But still, less is more. So you can do a typical scan with this dosage, which is appropriate. You could do like a fraction of that dosage and then use a deep learning program to generate contrast enhanced image. So you can submit this 10% dose scan to the computer. It'll make it look like a 100% dose scan. And that is really phenomenal. And actually there's a paper that came out recently last year that actually has a no contrast brain MR scan. That is coming. I kid you not. So hang on to your seats, everybody. It is going to be wild next year. Friends of mine in Japan did a GAN system, and they actually were trying to create synthetic flare images using a generative adversarial network. Why? Well, for speed, for one thing, better resolution. So I would ask you, which of these 3 images, they all look identical to me. One of them is a real flare acquisition we normally do. One is a completely synthetic image. And one is like a fabrication based on real anatomic data using a deep learning neural net. So is a synthetic MR for that matter. But you have 3 different kinds of ways to generate an image. And this was the real flare. This one looks the best, and that was actually the DL neural net flare. Okay. So what if you're going to go into this field for research purposes? Well, a few more things. We're nearing the end, so you guys are doing well for this technical radiology talk. The best projects in artificial intelligence, at least for patient care and imaging, are ones where you have a really clearly defined outcome. It addresses an important clinical need. And this concept of ground truth is really important because if we're going to advocate imaging, you have to know what the answer is. So if we take out a brain tumor and I know we're going to submit it for genomic analysis, I'll eventually get an answer. I'll know what the ground truth is. That's not always the case for a lot of medicine, which challenges us in the AI field. So yes, how do you analyze papers or literature or even products that are being available and marketed currently that use AI in imaging? Well, if it's about segmentation, you want to use the Dice coefficient, the degree of overlap, and that is excellent. So you want to have your Dice coefficient be more like this. For analyzing computer algorithms, what really matters are these sensitivities, specificities, positive and negative predictive values in the area under the curve. This area under the curve, where you map true and false positive rates. You want your curve to be something way up here, and that's probably better. However, the precision recall curve is also equally important, determined by true positives over true positives and false negatives. And so you can have a really good area under the curve, but if you don't have a lot of data, you can see that your recall curve is horrible. So both of those matter. And if you're analyzing, oh, hey, what just happened? 1 second. Let me go back to that talk 1 second. Hey. It did not like my using that page. Hold on, hold on.
Is everything okay?
Yeah. It's like sort of stuck for a second, the PowerPoint. So hold on. Let me try to reload it. 1 second. And 1 second. Okay. Let me just do new share. Is that good now, Joshua?
Yep.
Great. Sorry about that glitch. This is just showing you that we want to be both precise and accurate. The bull's on the upper left-hand corner. And this is called the loss function curve for convolutional neural networks. And as we said before, the more epochs you do, as you train and validate more and more, you'll have these curves you want to look at to see what your accuracy is for validation and how much information you've lost. And lastly, what I would say is that when you're looking at data, it really does matter the data that you give to your program. You don't want to have skewed training data. You have to be very careful about bias, make sure you have good gender parity, and that you have underrepresentation minority groups. You want to make sure there are no confounders. Like there's a very famous example of a computer program looking at chest x-rays, and it got every chest x-ray correct for detection of tuberculosis. When you went back to figure out why, it was because there was this little thing in the upper right-hand corner outside the chest x-ray saying TB clinic. So you have to be very careful about the data you give, and you don't want to overfit data like in this example, because you won't be able to use that program outside of where it was created, because it'll only work in your own little lab. So bias and ethics are really important. These are definitions from Webster Dictionary. They're not mine. And this is a real concern for artificial intelligence because it's going to be used in medical information and taking care of patients. So what's an example of this? Google, Amazon, all the tech companies have a pretty poor record of putting women in positions of leadership in their companies. And Amazon tried to do something to correct that, and they reviewed their own hiring practices and agreed that they had a bias, whether it was conscious or unconscious, they didn't know. So they created this program, and they used it to try to recruit more women executives and employees, and it failed miserably. This is just showing you how there really are not enough women in tech companies across the board. It should be more like the 50th percentile. It's far less. The problem was when Amazon created this computer programming, it was really biased to begin with, because what they did is they got data from hiring practices from 1970 to 1980, overwhelmingly male. So for example, if you went to a women's college, the computer program didn't recommend it. Those applicants were excluded. If you were involved in, let's say, the captain of the field hockey team that was a female sport, that was excluded. So this was a problem, and they had to actually reinvent it. Also, we have to be careful because already things like facial recognition is being weaponized all around the world, from Uyghurs in China to Rohingya, Myanmar. My wife was a diplomat for the UN and director of Asia. I can assure you this is happening. And we need to be very sensitive to this because we don't want to have AI programs develop that can weaponize medical information against patients. Here's an example where this can go awry sometimes. There was an IBM Watson initiative to develop an oncological artificial intelligence program. Memorial Sloan Kettering Cancer Center in New York City is one of the best cancer hospitals in the world, but it is a very unique institution, and therein lies the challenge. A quote from one of the doctors said that we are not at all hesitant about inserting our bias because I think our bias is based on the next best thing to prospective randomized trial, which is having a vast amount of experience. And that may be true, but what's true for Memorial Sloan Kettering is not how cancer care is probably practiced in 99.9% of the rest of the globe. So when this product was exported to Scandinavia, it failed miserably, and Denmark dropped it because it only agreed with the program a third of the time. In all the Asian countries where gastric cancer is a higher prevalence, it didn't work well, and they also abandoned the program. So it says that you have to really be careful when you input your data to know your disease prevalence and incidence, or it may not work so well. So all these little factors to keep in mind. I like this cartoon. The challenges of AI, like, yes, what happens to the computer? Will it be sued? No, actually, the radiologist, our eyes have to look at that AI program that's being used to interpret an image and see whether we agree or not. So we are still responsible. The big problem now in the literature is only 6% of articles have external validation, which is really important. 94% do not. So there's actually a lot of bad literature being promoted currently in that hype. That exponential curve is not always a good thing. So what are some of the challenges, for medical legally and ethics? I think going forward, there's a lot of discussion about a new IRB for the digital age. Like maybe if you have your images done, do you have a consent saying you can use those images to make an algorithm? This is not an unheard of concept. There are lots of consumer groups fighting this legal battle with Facebook and other social media companies, because Facebook essentially is a non-neutral platform. It basically has algorithms that are developed to get you to focus what you want on your feed, and they are making products based on data they accumulate from you, not necessarily with your informed consent, and that makes a product. Shouldn't you share in some of that profit? There's a lot of bias potentially, so to make sure that you have programs that are gender paritied and do have a good heterogeneity of population. That has been a problem in literature historically in medicine. For example, multiple sclerosis, most of those clinical trials were done on white Northern European women, which is why a lot of MS drugs don't work well in white males and Hispanics and Asians and African Americans, because those folks were not included in many of those clinical trials. There is a lack of large publicly available data sets because they're expensive and hard to do. Hospitals also know their data is valuable. Maybe they want to monetize that and sell it to a company or partner with a company. Bridging silos. I think one thing that's true about computer science, when I'm very active in this process nationally, and when we have people publishing, we really demand that they make their code available on GitHub so that other people can advance the science, because maybe they'll figure out a better way to do it, and that's good. That's how science should be working. But there is this battle, because most of us in this field want it to be a horizontal playing field, but there's still a lot of entrenched vertical hierarchy in medical research. Validating algorithms is expensive. There are some challenges now for the Radiology Society of North America. They had a challenge last year with 30,000 CT brains that had to be annotated. What that means is you had to have volunteer neuroradiologists around the world look at 30,000 CT brains to look for every spot of hemorrhage, hydrocephalus, midline shift. It's a lot of work. I mean, a person looking at 1,000 images, that could be 50 hours of work. That's not reimbursed. And if my employer knew I was spending 50 hours to look at imaging for a project, they might get upset if I didn't have grant funding to fund my time. And you want to have independent testing. We've already gone over that. If you're going to buy a program, now you may be involved in this process the next 4 to 5 years. You would want to know, where was that data coming from that was trained to train the algorithm? Was it collected under an IRB? You want to know about the patient population. Does it represent your patient demographic, right? Was any of the testing data used to train or validate the model? If that's true, you're going to have bias and an overinflated performance. Were synthetic images used? Was it trained in the entire image or just a piece of an image? How did they obtain their ground truth? And was performance evaluated at the exam level, lesion level, image level? And how was that performance proven? And was it proven on your patient demographic? You also need to ask, is it going to work with your IT infrastructure? Do they have a quality assurance program to maintain that it keeps working well over time? Is it scalable and ready for your enterprise or your healthcare network? And is it secure in terms of patient information, HIPAA, cyber secure? And really, is it integrated with your workflow? FDA approval is interesting. Many of the software companies that are in the AI space now, there are lower levels of FDA approval if you're going to just market it as an adjunct to my making a diagnosis as a radiologist. I think the big thing is that AI program useful? To be very honest with all of you, Dr. Ellis doesn't need a program to tell him that there's a hemorrhage on a CT. He's going to see it. I'm going to see it as the radiologist. If it's a very, very, very subtle hemorrhage, I'm not going to miss it. That's what I was trained to do. What I wanted to do, perhaps, is just change my workflow list to make me more efficient. So you really want to know, does it really enhance my performance and make it better? If it doesn't, it's not worth the investment. So if you get a program, run a test with your data, see the results and performance with your own eyes. The future of artificial intelligence is each and every one of you on this phone, because even if you don't go into radiology, it is absolutely going to be a part of decision support in every discipline of medicine going forward, no matter what you do, from pediatrics to obstetrics to surgery to medicine. It is in your future, and in pathology as well. If you're interested in artificial intelligence, there's a workshop that I run with a consortium of other radiologists in the country that are national and international. That is the website. I'm going to keep this slide up for a little bit so you can all look at it. We take 25 people. We go through a 2-day course. We hook you up with mentors, and then we support you on a project in artificial intelligence, and you present your findings in October and the fall. You don't have to have any computer background, because we have an online course that Peter Chang developed at UC Irvine Center for Artificial Intelligence and Diagnostic Medicine, and that'll be a part of it. But if you wanted to get involved, you don't have to, everybody's welcome. We want really, people who are interested in this field. So throw that out there to all of you. I'm always casting a big net to reel more people into radiology and artificial intelligence. I want to thank the members of the AI task force. This is a national consortium of neuroradiologists. I am the chair of this committee, and we are deeply invested in the promotion of artificial intelligence in radiology, particularly brain imaging and spine imaging, both nationally and internationally, because we do feel that this is the next big disruptive transformation of imaging affecting the country currently. I want to thank you all for listening. I think it's extraordinary that so many of you have stuck with me through the entirety of this program, and I'm happy to answer questions. And again, these are some references. If I don't get to all of them, send me an email. I think I included that. Did I not include that? Yes, cfilippi@northwell.edu. Happy to converse offline at any time with all of you. And for those in medical school, congratulations. Or PA school, whatever, nursing school, whatever school you're in, congrats. If you're an undergraduate, healthcare is like an extraordinary field where you can do a lot of great work for good people. And there are lots of roles for everybody. There are surgeons, there are medical people, there are people like me who look at images and do research. There's a role for all of us here. It's a big family of inclusion. So thank you for everybody. And I guess I can look at questions. Let me minimize this. Stop share. I need Joshua's help.
The chat right now has a lot of thank yous.
All right.
But if you guys could just keep the chat focused on your questions right now, that'd be great, so that Dr. Filippi could take a look.
Wow.
It's a lot though, so answer what you can in the next few minutes, and then they could email you as well.
Okay. All right. Wow. All right. I think it's great. As someone who's who's lived all over the world, I'm just really touched that there's so many people who are not from America who tuned in. It really, that to me is just makes me incredibly happy. I've lived in Europe, Nepal, Japan. I'm only half American, so I'm really happy to see this. Medicine's where it's at, you betcha, and radiology too. Hold on. Okay. Hold on. Malaysia, Poland, love it. That's great. Ecuador, all right. That makes me so happy. Me gusta, like it. All right. I'm just slow scrolling. It's because I'm an old man with bifocals. There were questions toward the end. Do I see AI replacing the radiologist? I mean, that's a very fair question. And many times when I go to a meeting and give this kind of lecture, there are people who are very unhappy. I'm just glad they don't allow fruits and vegetables into the lecture hall because they'd be thrown at me. So to be very honest with you, I think that currently there's a shortage of radiologists around the world. And absolutely in America, there's a shortage of radiologists, just not on the East Coast and not on the West Coast. But if you go to rural parts of New England, where I grew up in Vermont, there's a shortage. I was the only pediatric neuroradiologist for the state of Vermont for a decade. And there's there's one now, thankfully, but still. So this could be a way to augment healthcare in places that are struggling to find subspecialty radiologists. So it may be that it replaces some radiologists, but maybe in places where none exist currently. And I think that it will augment our intelligence. I really mean that. I think it'll make us better. But I think for us to be successful going forward, we have to embrace this technology, or otherwise we may be made irrelevant. So I think that I think is the really um, important piece. And then, you know, Phoebe and Marbid asked, well, what are some sources of literature that are neutral in AI and its impact? That's very interesting. I think if you wanted to learn about it, there's a deep learning book by Francois Chalet, and I can always send that to you. If you email me, Phoebe, I can just send you that book. It's a pretty good book on imaging and AI that's very neutral, that goes into how it works. And there's just, I think reading medical literature is a great way to do it. If you type in just AI and decision support, or AI and brain imaging, AI and whatever kind of imaging, MRCT, it's pretty good. I think it's out there. It's an evolving and emerging field.
Are you okay? Are you okay if I send your email out to all of them?
Yeah, that's fine. For the Northwell one, is totally fine. Yeah, Josh, you can totally do that. It is true that companies are, yes, recording. I know. Thank you, Shrikar Valuri. You are correct, and it does bother me. That's why I'm not on Facebook. We can talk offline about that. Now, this is a great question from Samira Malik about, can AI predict a cancer beforehand? There was a great paper I want you to look up by Linda Moy, M-O-Y, Linda. It was on mammography at NYU, Langone. If you go to PubMed, you should be able to find it. They looked at 1 million mammograms, and they did a convolutional neural network. And they were able to predict in January, based on mammograms, which ones would convert to cancer 9 months later. So that is happening as we speak. So I think breast imaging, I didn't talk about, but it's certainly a hot topic, because you have great data, because there's a thing called the mammogram, there's an MQSA Act, which is Mammogram Quality Standard Accreditation or something like this. But there's basically federal guidelines that are very strict with mammography, where you keep track of every biopsy and whether you were accurate in terms of predicting cancer. So every mammographer in the country knows their true positive, false positive, true negative, and false negative rates on mammograms. And there's actually a number. You have to be within a certain percentage. And if not, you have to go back for more education. So this does exist for breast cancer, for sure. And now they just do it just to test it prospectively, because that was sort of I think a retrospective study. The key thing about that paper was they also had a lot of clinical data, and there were things which were shocking to them, like a thyroid hormone level was a good predictor of transformation to malignancy 9 months later. That was really earth-shattering to me when I heard it, because a thyroid function is a simple blood test. It costs $1. And if it was something that cheap and inexpensive was better at predicting transformation from a mammogram, I mean, that is really groundbreaking. So we have a lot of work to do. Yes, Jacob Steele yes, you are correct. There's going to be a lot more artificial intelligence training in the future. That's why we have the task force in radiology currently. There's one for every imaging society that I know of. There's a tremendous amount of work ongoing currently to train the next generation to take over the mantle, because a lot of us in this task force, we're in our 50s, and we want desperately to pass the baton and mentor other people. So yeah. Oh, so ground truth, Michaela Lyons, I'm really sorry. So whenever you're developing a model, let's say I wanted to predict whether a brain MR scan showed a tumor, and you gave me 100 images. For every one of those images, I would have to make a prediction. Tumor, yes, or maybe it's stroke, yes, or multiple sclerosis, and I'd have to do this. Well, if I predicted on this one image, I think it's a tumor, the ground truth is what that image really was, which was already dictated by a neuroradiologist that said it was a tumor, or it was removed and it was a tumor. So that's what we mean by ground truth. Someone answered your question, I'm sorry. I think it's a really good idea, Andre Youssef, I think it's a really good idea for anyone going into medicine to be at least versed in artificial intelligence. If you want to go into radiology, I think it's even more important to learn some computer programming. But I think for everybody going into medicine, I think understanding AI would be helpful. Most of you on this call who are young are already so much more fluent and savvy in the medium of computer technology. you know, for people my age, 55 and over, I'm like a total outlier, and that I really am into this space. That's just not typical. So I think that many of you who are very fluid with social media, this is really good. You're going to probably have a much more easy time incorporating this into your practice. Yeah, I really do think that AI benefits far outweigh the risks. I think that things like security are relatively easy. Um, I think cost will be dropped dramatically going forward, and bias can be controlled as long as we're aware of it. Um, uh, yeah, nanotechnology in medicine is another talk. I am not an expert, but I do know that that's really critical for drug delivery development. Um, I do not know enough about Neuralink, but if it's a repository of imaging that people can use for this, absolutely. No, you do not have to be a rad MD to do AI. Lots of thank yous. You're all very kind. Okay, you're all very, very kind. Wow. Lots of thank yous. Yeah, Nicholas Daddario, I'm nearly done with these comments. Yeah, I mean,
Yeah, we can cut it off here if you want. They could all send you emails with the rest of their
yeah,
questions.
so Nicholas Daddario, send me an email. That's a really complicated topic, but you are correct. I want to thank you all very much. I hope you all have a great day. And yeah, reach out. And if you're interested in AI, I'm happy to direct you to the right places. And thanks.